Yeah, so let's start with the first problem. Or not the first problem. This is the first problem from the lecture problem section. So the problem is, let's see, you have, this is number 28 on the handout. So you have a triangle, and then, yes, maybe let's write everything down. So ABC is a triangle. IA is the A excenter. Okay, so you guys know what the exicircles are? Or, I mean, have you seen them before? I can maybe give some review if you haven't. But have you guys seen the exicircles before?
Yeah.
Okay, so IA is the excenter, and then X is the intersection of the AX circle with side BC. And then what? So, and then D is on BC such that CX equals DB. So let's at least maybe draw this part first. Okay, maybe we'll draw the whole thing. So then show DIA and XI intersect at the midpoint of the altitude from A. Okay, so let's try to draw some kind of picture first. So we have the triangle ABC. And we have also so there's a circle here, which is tangent like this, let's say. So this is IA, and this is what they call X. And then there is a point D, which is here. So, and the key thing is CX equals DB, right? So they're reflections about the midpoint of CB. So before we continue, let me ask, what really is D? So D has this strange condition, but let's really ask, what is D? There's maybe a better way to think of the point D. So this is where you take the tangency point of the exicircle with the nearest side, and then you reflect over the midpoint. Whenever you see this, you should think it's actually something else secretly. You guys know what I'm getting at? So I'm claiming this point D really, it has a different interpretation. So did you guys understand the question?
Yes.
So, okay, I guess I'll say. So my claim is what D really is um, if you draw the in circle. Okay, I'm doing a bad job of drawing it, but okay. If you draw the in circle, it will be tangent to BC at D. So what is D? D is the intersection So have you guys seen this? Do you guys know this lemma that if you look at where the in circle intersects, like so if you look at where the in circle, oh, that's not what I want. If you look at where the in circle intersects the side and where the exicircle of the opposite vertex intersects the side, they're reflections about the midpoint. Do you guys know this fact? Have you seen this before?
I've seen
Um,
something similar with the orthocenter and the incenter and the exocenter.
The orthocenter, the incenter, and the excenter. So there's
So they're
something.
like reflected. It's
So
like
I think
reflection. Yeah.
so that's what the orthocenter, the centroid, and the circumcenter.
Yeah. The centroid motif. Yeah.
Yeah. So that's something a little bit more sophisticated. This is actually very this is a much simpler fact. So maybe let's prove this fact. So um yeah. So what is the claim? So this is an important thing to know, that if I draw the so this is a lemma, I guess. This is an important lemma. Um, that yes, if I draw the incircle and if I draw the X circle, and I look at the tangency point, so this is D and this is X, then CD equals BX. So this is the claim. Um, so do you know how to prove this?
yeah,
Yeah, so how would we prove this?
I I actually proved it while studying from Evanton's book, I think yesterday.
Okay. Yeah, okay, good. So yeah, maybe I can just briefly say what is the proof. The point here is, um, this length CD you can actually calculate. So let's say the sides of the triangle are ABC. So triangle has sides ABC. The point here is, okay, let's just maybe call this E and this one F. So, um, if you forget about the X circle for a moment, you say, okay, if you just think about what are these distances. So like, what I mean is this one, this one, this one, this one, this one, and this one. So how does the in circle cut up the size of the triangle? You can just calculate very explicitly, because this side and this side are the same. This side and this side are the same, like there's two tangents, right? And then this side and, okay, just to be a little bit clear, I mean, this thing here, these are all the same. Does it make sense? So, uh, what does it mean? It means x plus z equals a, x plus y equals b, and y plus z equals c. Um, and so when you solve this, you'll get, okay, you'll get something very exact. You'll get maybe x is equal to a plus b minus c over 2, y is equal to minus a plus b plus c over 2, and z is equal to a minus b plus c over 2. Does it make sense, what I'm saying?
Yeah.
Yeah. And okay, and the argument for, okay, so that's how the in circle cuts up the sides. And there's a similar argument for the x circle. For the x circle, what are we asking? So for the x circle, now we're looking at something like there's okay, so what we're looking at is how these cut up the sides. So there's here there's a length here which is like, maybe call it capital X, capital X, Y, Y, and then there's Z. Okay, let's use different letters. Let's call them. Okay, yeah, let's call them. Okay, I'll still use the same letters, but I'll write it in blue, right? So hopefully it's clear. Um, so capital X, X, Y, and then Z, and then Z. And then the equations here are something like, okay, um, capital X plus capital Y equals A, capital Z minus capital Y equals C and capital Z minus capital X equals B. And if you solve these, you'll get something like this time capital Y is equal to maybe minus A plus B plus C over 2. Okay, and some more. So does it make sense? And you can just show like the point is okay. Then what? Little x equals capital Y. So I wrote the wrong thing. Maybe what I meant is yeah, what I meant is this. Yeah, okay. Yeah, it's not maybe it's not worth doing the entire thing, but you can do this exercise and what you'll find is that CD equals BX. Does it make sense how you would prove this?
Yeah.
Okay, yeah, so this is just an important lemma you should know. Okay, but Kareem,
Uh,
do you have a comment, Kareem?
yeah. Yeah. Um, what's that name? The tangents of
What's
uh
the name of?
the x circle. Let's just name them the tangents of the x circle on AB and AC. Um, let's just name them anything. B prime, C prime, or anything.
Uh-huh.
So we get that A B prime equals A C prime, which equals the semi, which equals us, or which equals X plus Z plus Y.
Are you proving this statement or?
We can prove it since
Okay,
um
okay, so you're giving a proof here. So you're saying, yeah, so which one? So yeah, so you're calling which one B and which one B prime?
um the right tangent B prime, the left tangent C prime.
So this is B prime. Um, maybe let's use a different color. This is maybe black. This one you're calling B prime. This one is C prime. Okay, and then you're saying what?
No, I mean the tangents of the X
I see.
circle.
I understand that. So you're calling this one is B prime and this one is C prime. Okay, great. And now you're saying,
And I'm saying um since we have a B prime equals a C prime, then we know that a they equal their sum divided by 2,
mm-hmm.
which in turn equals um Y plus Z plus Y capital um plus Y plus X capital, which also equals um the the perimeter of the triangle.
Hmm. Y, little z, little y, little x, and then capital. Ah, yes, this is the semi-perimeter. Great. Yes. Yes. Okay. Yes.
Yeah, we can use this to prove what we proved above.
Yeah. Yeah. So then you can prove. And I think yes. What I mean, maybe you can just write it down. So what the conclusion will eventually be is that. Yeah, so it's what you said. Um, capital Y will be A plus B minus C over 2. Capital X will be A minus B plus C over 2, and then capital Z will be the semi-perimeter. I think. Okay, maybe I'll leave the rest of it to verify this as an exercise. Is that okay? I think it's it's just some kind of linear or some kind of playing with equations. Does that does that sound good?
Sure.
Um, yeah, okay. Let's just take it for granted now. Great. Okay, so the whole point of this was, okay, really you should think of D as this intersection of the in circle with BC. And now what? Now we want to show that now we want to show that if I take, yeah, so we're looking at this now. We want to show that DIA and XI intersect at the midpoint of the altitude from A. So we want to look at basically this point here, and where these are equal. And we want to show that, so DIA and XI. So if I were to draw I is here. So we want to show DIA and XI, these two lines, their intersection point is the midpoint of the altitude. So they intersect here. So I think what, yeah, so let's do something a little bit different. What I'll say is, so I'll rephrase this slightly. I'll say, let's say, let's call it Z. Yeah, let Z be the midpoint of the altitude. And so the point of this exercise is to really show that, X, I, Z are collinear, and D, I, A, Z are collinear. So yeah, this is equivalent. Does it make sense how I've rephrased this?
Yeah.
So this relates two problems, and so yeah. So what I'll focus on maybe one, okay, and then I'll leave the other one as homework. So let's show that X, I, and Z are collinear. Yeah, we can maybe simplify the diagram a little bit. So yeah, so maybe I can even phrase it like this. So um, so what are we doing? We're saying that we have a triangle, we have a couple of things. We have its in circle, and then we have its X circle. So these are imperfect pictures. So you have X and you have I, and then you have this altitude. So we want to show what? We want to show that X, I, and the midpoint are collinear. But again, I think maybe another way of doing this that will be useful is instead think about, maybe define Z prime as the intersection of Xi and the altitude. And we want to show that Z prime is the midpoint of the altitude. That's what we want to do. Okay. Does that make sense? Is that so? This is a slight reformulation of the problem, but okay. Are we okay with this formulation?
Yeah.
Okay. And so here is where so this is now. So what I'm going to do now is the following. there's a very nice trick here. Or there's okay, sorry, that's not what I meant to do. Yeah, so there's a so in this config, when you see something like this, there's a second lemma that should come to mind. Okay. And the lemma here is it's not a lemma, it's an idea. The idea here is in this configuration, there is a particular dilation. So there's a dilation in this picture that's often very useful. So do you guys know what I mean by a dilation? It's a geometric transformation that's centered at a point that stretches things. Do you guys understand what I'm saying?
Yeah.
So in this, whenever you see,
I don't get what dilation means.
you do or do not?
Do not.
Okay, so a dilation it's a geometric transformation, so a rotation is a transformation where I have a center and then I rotate. So a dilation is a transformation where I have a center and then I stretch. Um, so yeah, what is a dilation? Let's draw a picture. So it's like um, so I have a point. So this is the center of dilation, and then I have a ratio. Maybe this is a ratio, some ratio. Let's say maybe 2. It can be something else. So the point is every point now. So if this is my starting point, then after I dilate, it becomes like this, twice as far. Okay, so like the whole,
Oh, alright.
does it make sense what this, it's a geometric transformation, that's a
Yeah.
stretch. Okay, and the other word maybe people use is homothety. Maybe this is the word that, are you familiar with this word more maybe? Homothety.
Yeah, I've heard of it.
Yeah, okay, so that's the key idea here. So there's a dilation or a homothety in this picture. Can you guys find it? So this is a very important exercise. So maybe I'll call it the so idea. This is the key idea. This is the in-circle. I don't know if that's what it's actually called, but the in-circle x-circle homothety. So the point is, what is the center of the dilation? Oops, that's not right. It's A. Okay. So the point A, there's a dilation that sends the in-circle to the x-circle. Do you see it? Because what are the in-circle and the x-circle? They're just two. They're just, I mean, they're just two circles that are along these two rays, and they're tangent to the two rays, right? So there's a dilation that sends one to the other. Does it make sense what I'm saying?
Yeah.
So maybe I can draw it in blue or something. So so what do we have? If we just look at A, so A is here, and then we have two rays coming from A, and then we have here we have the in circle, and here we have the x circle. Okay, so there's going to be some homothety centered at A that turns the in circle into the x circle by some factor. So, and what is the factor? Okay, maybe I'll just write it explicitly. So I and IA, these lie on the same line as A, or they're collinear with A. So I say consider dilation centered at A with factor IA over I. Okay. So this should send the in circle to the X circle. Does it make sense what I'm saying?
What was the last part?
So what is the claim? So this dilation, this dilation sends the in circle to the AX circle.
Oh, okay.
Does it make sense?
Yeah.
So, and in particular, what it means is that if I draw this guy here, so this is the tangent to the in circle that's parallel to BC. Okay. There's going to be a point here called E. Okay, and so this is parallel to BC. How do I mark this? I'll mark it like this. Then these points are on a line. Okay. So maybe I can draw slightly. So I have a diagram of this. Maybe I can share it. This is the diagram I'm missing. So it's this here. Do you guys see? So okay. So their B and C are flipped from mine, but nonetheless, it's the same picture. So the point is, what they added is this line, which is parallel to the side of the triangle. So it's, this is parallel here. And then they're saying that these points, the intersection point X and A are collinear, because the reason is the dilation sends E to X. Does it make sense?
Yes.
So this is the key idea, right? The dilation sends E. So yeah, let's maybe draw in the rest of the picture. So remember, the rest of the picture was what? We have this altitude, and we draw in now xi, and this intersects at z prime, right? And what we want to show, right? So what we want to show is that z prime is the midpoint of the altitude. Right? So this is our goal. Yeah. Do you guys remember? So remember this, it's the same picture as before. But now what can we do? Well, now because of the dilation, there's this very nice triangle we have here. We have this, right? And yeah, so the point here is we can check, check that ED. Okay, so first of all, AEX are collinear by let's call it the dilation lemma. I don't know what to call it. That's not a technical name. And then we also have ED is parallel to the altitude, right? And that's just because they're both perpendicular to BC. But then, I is the midpoint of ED, just because, it's a diameter and that's the center. And so actually, it tells us what? So we have, let's call this guy, I don't know, what should I call the foot of the altitude? Maybe I'll call it K or something. Yeah, so we have these two together gives us triangle AKX is similar to triangle EDX. So, and then since I is midpoint of ED, it shows Z prime is midpoint of AK. Does it make sense? So, okay,
Could you repeat the last part?
so did this one make sense? I have AKX and EDX are similar.
Yes.
So then what? Then I'm saying, okay, so then it's an observation that I is the midpoint of ED. Does that make sense?
S- I is the mid. Yes.
Right, because it's the center and the ED is a diameter.
Right.
And then so then that gives you that Z prime is the midpoint of AK.
I see. Okay.
Right? Because what am I mean, let's maybe just, yeah, so let's isolate the picture a little bit. What is this picture here? I mean, I have AKX, some kind of right triangle,
Sure.
and then I have this ED, which is some parallel line to the to the to the to the to
AK.
AK, right? So now if I have this thing where this is a midpoint, then this is also going to be a midpoint. Just I mean, I'm saying this
Uh,
ratio, I'm saying, what am I saying? I'm saying EI over ID equals a Z prime over Z prime K,
right.
right? And yeah, it's some kind of standard
Yeah.
exercise, yeah. And so it tells us Z prime is the midpoint of AK. So does it make sense?
Yeah, makes sense.
Yeah, so really, I mean, this okay. So we've done half of the problem, right? So remember our original problem. Yeah, there's a big problem, but remember, so what did we show? We showed Z prime I and X are collinear, or rather, okay, we showed Z prime is the midpoint of AK, which means that Z, I, and X are collinear. Um, right? Yeah. So we've shown half. We've shown that Z, I, and X are collinear, and so we have the other half as well. So let me now I'll ask, do you want to do you want to see, do you want me to do this now, the other half, or do you want me to leave this as an exercise? So this part, D, I, A, and Z are collinear. Do you want this to be an exercise, or do you want it to be should I show now? The argument is very similar, but you have to sort of, there's another dilation you have to find, and you have to use it cleverly. And okay. So I'm asking you guys, should I do this now, or should I leave it as an exercise?
I think an exercise. I think I need to solve more geometry.
Okay, good. So okay, then I'll leave this as an exercise. In that case, please ask me if send me some kind of message if you get stuck. This argument, is important to know. Okay. Yeah, so maybe I'll just write it. Yeah, so this part will be an exercise. Okay. And maybe I'll also say number 29 can also be exercise, and number 29 can be an exercise. Because I think number 29 is a very similar problem. Yeah, okay, maybe it's kind of similar. Okay. So now what did I want to do? I wanted to do number 30. Yeah, so let's look at number 30. Let's look at number 30. So so H, so ABC is a triangle, H is the orthocenter, and then we construct these two circles, no, maybe three circles, right? So we have, I will say gamma A is centered at midpoint of BC and passes through H. Okay, so they're defining a circle by telling you the center and telling you a point that's on the circle, right? And then they're saying gamma A intersects BC at A1 and A2. Okay, and then similarly define B1, B2, C1, C2. Prove, and the problem is to prove that these 6 points A1, A2, B1, B2, C1, C2 are concyclic. Okay, so let's draw some kind of picture. So I'll just do a sketch now. I'll give a better picture later. So let's say A, B, C. Just let me make sure my picture is correct. So yeah. Okay, so then, and then what? So then we have the orthocenter. I'm just gonna mark it H. I'm not gonna draw all the altitudes because I think it'll clutter the picture. And now, yeah, so we have this orthocenter, and now, so yeah, let's construct. So actually, I'll construct B1, B2 first. So we have this midpoint here. Let's call this one is E, and this midpoint here, let's call it F. So so first we have this circle that goes like this. So this is gamma B. And these are B1, B2. I don't, yeah. And then we have gamma C like this. So this is F, this is gamma C, and then C1, C2. Okay. Okay. And I won't draw A1 and A2, but you know they're defined somewhat. So we want to show that these 6 points, yeah, we want to show that these 6 points, something like this, are concyclic. So yeah, so any ideas how to get started? Or maybe say is there something that's slightly easier to show than the full showing that all 6 points are concyclic?
Maybe you can show that for from our cycler.
That's right, yeah. So the first, you know, let's just start by showing let's start by showing that 4 are concyclic. And okay, a natural choice for 4 of them is just well, the 4 that I drew, like you just take 2 pairs, right? So let's start by showing B1, B2, C1, C2 are concyclic. Okay, and then we'll worry about all 6 of them together. Great, so we should start there. And now, and so now, yeah, so this is some kind of fairly common situation in geometry. So we have these like we have these 4 points. But there's something special about these 4 points. Namely that each pair, so there's 4 points, there's 2 pairs, each pair actually lies already on a circle. That's given to you, right? So is there some way to rephrase this concyclicity condition? So you know, maybe usually when you show concyclicity, you do some kind of you have to show some kind of angles. Like maybe you do, okay, maybe you say I want to show this angle is equal to this angle, okay? Or you want to show that this angle and this angle add up to 180 degrees. That will be kind of hard in this situation because it's hard to get like any kind of control over these angles. Okay. So what I'll say is in this case, there's a very clever way to show concyclicity. So any ideas how to do it? So what I'll say is it's one of these exercises from section 1, configurations in geometry. So let me just repeat the situation. So what is it? We want to show so we're in a situation where we want to show that 4 points are concyclic. And we know that B1, B2 are in one circle, gamma B, and C1, C2 are in another circle, gamma C. So when you're in a situation like this, there's some clever way to show concyclicity. So, yeah, so this is the sort of the trick I wanted to show. So do you guys know this radical axis theorem?
Yeah, but I'm sure how we can prove that they both their intersection lies on um yeah, I wasn't sure how we can prove this.
Well, so how would you use radical axis theorem here?
Um so we just prove that B1 C2 or the intersection of B1 C2 and C1 B2 lies on the radical axis of both circles, and this will prove that um, B1, B2, C1, C2 is cyclic quadrilateral.
Okay, so you're saying, yeah, so what, okay, maybe we need some more space. So, let me duplicate this. Right, so what you're saying is maybe by technically the converse of radical axis theorem. What we would want is, so we have a circle here and a circle here, and we have these points. And no, that's not right. And then we want to show these are concyclic. So you're saying that you want to show that this one and this one intersect on it's not it shouldn't be quite that, right? So for radical axis, we want to show that the radical axes of each pair intersects, right? So what you would want to show is that um, uh, this one and this one intersect on the radical axis. Does it make sense what I'm saying? So Kareem, does it make sense? So it's not that you want C1 B2 and C2 B1. It's you want C1 C2 and B1 B2.
Oh, so it doesn't matter what which pair we choose.
No, it does. It matters which pair, right? It does matter, and you want. I mean, okay. Well, what does radical axis say in general? It says that if I have three circles, I have to take their pairwise radical axes. So I have to take this one. Okay, sorry, these are bad pictures. It says that I consider the 6 points of intersection, and then I take the pairwise axes. So I take this one, and this one, right? They will intersect. But in our case, where there's a circle here, and a circle that looks like maybe it's bigger, but it looks something like this. Okay, maybe that's I want to draw a different circle. Maybe something like this. But I still need to take, I can't, I have to take this one, right? Because that's the axis. Do you see what I'm saying? And I have to take this one. And I have
Oh,
to,
okay, I understand.
you see, so yeah, you cannot like this is not allowed.
Yeah,
Yeah. So it really has to be those two. So does it make sense now?
yes.
Yeah. So okay. So what is the whole point? The point of this? It's that radical axis tells you that what we're trying to prove. So this is the converse of the radical axis. Tells you that showing that B1, B2, C1, C2 are concyclic is equivalent to saying that B1, B2 and C1, C2 intersect on the radical axis of gamma B and gamma C. Okay,
Yeah, this should be easy to show.
that's right. So
Um,
point, uh-huh.
yeah, we just connect E and no, so the radical axis should be um perpendicular to EF, and EF is parallel to BC.
Great. Yeah. So let's just, yeah. So the picture, here's the picture, right? And yeah, like you said, it's very clear. So, yeah. So what is the picture? we observe EF and BC are parallel, so right, so so I think you said it right. So radical EF is parallel to BC, and then radical axis is perpendicular to EF because it connects the centers of the circles, and so yeah, so it tells us XH is perpendicular to BC, so A is on XH. Or maybe I'll say it like this. So XH is the altitude and A is on XH. Okay. Good. Yeah, so it's a very, very clean argument. So there are any questions? Does it make sense?
Yes.
Abdullah, does the argument make sense?
Yeah.
Good, yeah. So this is a very clever usage of the radical axis theorem. It's to show consequently. Okay, good. So yeah, so that was a nice problem. And I think we'll have time for one more. And so,
But we're still not done with this problem.
oh, that's right. I completely forgot. We haven't finished this problem, right? So yeah, that's good. So let's finish the problem. So what was the whole thing we needed to do? We needed to show.
Yeah, we had also A1 and A2.
That's right. Okay, great. So, yeah. So we showed that yeah, B1, B2, C1, C2 are concyclic. So, of course, yeah. So what have we gotten ourselves so far? So by symmetry, so yeah, B1, B2, C1, C2 concyclic. By symmetry, A1, A2, B1, B2 concyclic, and so is A1, A2, C1, C2 are concyclic. Okay, so maybe it's a little bit messy to draw, but you should imagine that, okay, among these 6 points, if I take them in 4, and like, so among these 3 pairs, if I take them 2 at a time, they'll be concyclic. And now I just want to show that, so I have these 3 circles, and I want to show that they're the same, right? That's the idea. I have these 3 circles, and I want to show they're the same. So any idea how I can do this? Yeah, so I have these. It's a little bit annoying to draw. Maybe I can try. Okay, the problem with drawing it is that three circles will be the same. So, um, so maybe I'll ask this question. This is just some kind of trick, right? I'm sure there's other ways to do it, but here's one way. Let's say the 3 circles are different. Okay, so let's say these are 3 circles, 3 different circles. We'll call them omega 1, omega 2, and omega 3. So here's my question. If they're different, what is the radical axis of omega 1 and omega 2?
Yeah, it's the altitude.
No, that would be for gamma and gamma, for omega and omega, right? So this is it's a little bit. Did you see? Like neither what you've given me is the radical axis of gamma B and gamma C. Do you see what I'm saying?
Oh, I think.
Like omega 1 is this circle here.
Oh,
Oops, right. Omega 1 is this circle that passes through B1, B2, C1, C2. So I'm asking if let's say that B1, B2, C1, C2 and A1, A2, B1, B2 are not the same circle. Okay, then they're different and then they have a radical axis. So it's a bit hard to draw because it's false, but imagine you had yeah, so you had one circle like this passing through these 4 points, and then you had another circle, I don't know, in red, let's say. So that would be this one, and then you had another circle like this. Okay, that passes through these points. Okay, so the point is their intersection points would be B1 and B2. So the radical axis would be B1, B2. Okay. So if they were different, so I'll just so yeah, that's right. If omega 1 and omega 2 are different, their radical axis is the side AC. Does that make sense? Or maybe it's called B1, B2. And this is
yeah.
because yeah, because B1 and B2 lie on both circles, right? Okay, so but now the point is, okay, the three radical axes of the pairs don't intersect at one point. I mean, they're just, yeah, like they're not concurrent, so they can't be different circles. Does this make sense? It's a contradiction because B1, B2, C1, C2, and A1, A2 are not concurrent. Does it make sense what I'm saying?
Yeah. But how do you prove that circles aren't um that they aren't all in line?
The cycles, the circles. Sorry, I don't understand what the
Yeah, the
concern is.
three circles.
How do you know that they're not what?
How do you know that they do not lie on the same line?
Ah, you're saying there's a situation like this. So is this the concern that you have a situation like this where sorry, like this where the three axes would be parallel?
Yeah.
Because the radical axes are not parallel in this case, right?
Oh, yeah.
Right there. I see. So that's a good point. So they don't intersect and they're not parallel. That's the thing. Wait, yeah, here. Yeah, so the main point is that yeah, B1, B2, C1, C2, A1, A2, they don't intersect and they're not parallel, so it cannot be that the circles are different. But yeah, that's a good point. I didn't think of this. Okay. Okay, so does it make sense now?
Yes.
And so for this last step, I'm sure there are some other kind of arguments. I didn't think so carefully about it, but this is one. Main tough part is showing that 4 points are concyclic. Okay, so let's go now to the other problem I wanted to do. So this is number 33 on the, yes, this is number 33. Let's see, where is the, do I have the problem somewhere? Yeah, so it's this one here. So you have triangle ABC. Let me list, there's a lot of information here, so let's list all of it. So you have triangle ABC, and then you have, by the way, this is number 33. And then you have circle gamma, and you have orthocenter H. Okay. And then what? So now, yeah, so now there's this point K that comes. So K is an arbitrary point. So K is completely arbitrary. So K is, it's an arbitrary point on the circle. So K is a point on the circumcircle. Now it says on the other side of BC from A. Okay, so it's, maybe I can just, maybe there's an easier way of saying this. It's a point on the circumcircle on the arc BC. But okay, maybe on this small arc BC. Oh, but it might not be the small. Okay, on BC, not BAC. Let's say it like that. Okay, and then we have K and L. Oh no, then we don't. Then we have just L. L and M is what we have. So L is the reflection of K about AB. Okay, so yeah, so from K to L is like this, it's over AB. And then from K to M is over BC, right? And then there's a point E. Well, there's a lot of points here. So how does E occur? So E is the intersection of gamma. Okay, I think I need more space for this. Oh no, that's not what I wanted at all. Sorry, this is E is the intersection of gamma with the circumcircle of BLM. Okay, and then what is the problem? So the problem is now to show KH, EM, and BC are concurrent. So it's basically this thing here. We want to show this concurrence here. Okay, so KH, EM, and BC. So does the problem make sense? Yeah, does the problem make sense to everyone?
Uh,
So yeah, so this problem is there's yeah, at least to me the statement is a little bit, I don't know. KH and EM are kind of random looking to me. There's a way to simplify the conclusion here a little bit. So maybe I'll give you some time to think about it. Um yeah, there's a way you can simplify this statement a little bit. I don't know, this KH and this EM are some kind of, especially EM is some kind of really strange kind of thing. And, showing concurrence is kind of hard. Um, there's an important lemma involving the orthocenter and the circumcircle that's relevant here. Do you guys know what this lemma is? So it involves the orthocenter and the circumcircle. These guys here. So it's yeah, so it's actually it's problem 7 in section 1.1 of this handout. So it's this thing here that if I take this orthocenter and I reflect over BC, so I take this guy and I reflect it over BC, I'll get this point H prime, and H prime actually lies on the circumcircle. Do you guys know this lemma?
yeah.
So actually it also lies on the altitude as well. Well, look, I mean, that one may be clear, but yeah, okay. Um, um, yeah, yeah, so yeah, so how can we use that here? Yeah, so remember the relation between K and M is reflection over BC, and that's the same as the relationship between H and H prime. Yeah, so we're trying to show that KH, EM, and BC. Maybe another way of saying that is we're trying to show. So maybe I'll slightly rephrase what we're trying to show. So, so what we want is that KH and EM intersect on BC. That's another way of saying what we're trying to show. Yeah. Somehow I want to reformulate that using the fact that okay, K and M are reflections of each other, and so are H and H prime. So any ideas? Or another alternate approach. I mean, looking at this picture, is there anything you think might be true? You know, some kind of interesting observation that might be true. Okay, so maybe I'll say this. So how do we use this H prime? The point here is, we want to understand what is this intersection point, right? Like, what is this we have all these things. What is this intersection point? So it's where KH intersects BC. But because of this reflection property, KH actually intersects BC at the same point that MH prime intersects BC. So let me just write what I'm saying. I'm saying that, so this is a claim, I guess, right? So maybe I'll call it a claim. KH and MH prime intersect on BC. Does that make sense?
Yes.
Right. So KH and MH prime intersect on BC. So what that means is that this claim that we want to show is actually equivalent to showing that E, M, and H prime are collinear. Does that make sense? Like I want to show that EM also passes to this special intersection point, so I should just show that EM and H prime are collinear. Does that make sense?
Yeah.
Okay, good. So that's the first key point. Okay, great. So what do we do next? So what do we do next? So okay, so now what I'll say is this. Yeah, let's do this. Let's look at how we constructed everything. So we started with K, which was, yeah, so everything started with K. Okay. And then we got from K, we got this L and M and some kind of fairly, okay, we reflected two things. And then what did we do? We came this E. So what is this E? This E is something kind of strange because this E is you take BLM and you intersect that circumcircle with with gamma, with the circumcircle APC. So E for me is kind of a strange thing. So I think a better way of phrasing all of this is instead, okay, so we want to show that E, M, and H prime are collinear. So I think a better way of saying all of this is let's instead let's take M, H prime, because we already have these points. Let's say this intersects the circle, the circumcircle gamma at E double prime. Okay. And then we show that B, L, E double prime, M, B, L, M, and E double prime um, are how do you say concyclic, right? So let me let me write that. Yeah, so what is the idea? What is the strategy? So sorry, I need to just redraw the diagram. So what am I proposing? I'm saying um, I think it's here, right? So no, it's not right. Okay. So I'm saying, right, so first we have H prime here. And now we sort of forget about E and we say, okay, we let this be E double prime. So define, oh, so just one prime is enough. E prime is the intersection of MH prime and gamma. Okay, the circle of ABC. I want to show that B, L, M, E prime are concyclic. Okay, I think this is easier than what we had before, where you have to sort of intersect some circumcircle with another circumcircle, and okay, that's something a little bit stranger to me. But does it make sense does it make sense this is a valid reformulation?
Yeah.
Yeah, so this is this idea of phantom points. So now, so what's the idea now? Um, yeah, so what's the idea now? Mm, well, yeah, so let's remind ourselves how these points M came. So M came like this. And L came like this, right? Where these are reflections. So now, yeah, so now I'll say, yeah, so there's a lot of ways to show concyclicity. In this case, I think maybe it's easiest to show some equality of angles, but the question is which angles, right? So what I'll say is there's some angles in this picture that are kind of easier to calculate. Yeah, so for example, So maybe I'll give a suggestion and then you can think about it. Let's use a different color. Let's use don't know, maybe I can use green or something. So I claim this angle, because of how L and M were constructed, is easy to calculate. And so then to show concyclicity, you would compare it to this angle, right? You would compare it to this guy. Um, yeah, so this is equivalent to saying that angle L E M, which is also angle, maybe LEH prime is a little bit more natural, is 180 degrees minus angle LBM. Yeah, but I claim you really can calculate angle LBM in this case. Do you guys see how to calculate this angle LBM? Okay, so actually, do you guys understand what I'm doing right now? Like why? So I'm trying to show concyclicity by comparing these angles. Does it make sense? This is E prime, sorry. Okay, are you guys confused?
Yeah.
Okay, let me see. So do you understand the strategy of using E prime instead of E? Is that clear? Because maybe that's the confusing part. So remember what were we trying to show before? So what we wanted before was, or okay, what we want to do, we want E, M, and H prime are collinear, right? So that this is right. So this is because like we showed that MH prime and KH intersect on BC, to show that MH prime, to show that EM and HK intersect on BC, you just have to show this. So is that okay? That this showing that EM and H prime are collinear is equivalent to solving the problem. Okay.
Oh, okay. No.
Does this
I
make
think
sense now, or sorry?
I think that,
Yeah. So the problem is equivalent showing that EM and H prime are collinear. And then what I'm saying is it's this E is sort of a weird point. So what another approach is to actually say E prime. So this is the phantom point, which is supposed to be the same as E, but you say E prime is the intersection of MH prime and the circumcircle of ABC. And then you want to show that BLM E prime are concyclic. Does that make sense? So this would actually be the same as showing that EM and H prime are collinear.
yeah,
So that makes sense, yeah?
yes.
Okay, so now I'm saying if you want to show this, so you forget about this dotted circle, it doesn't exist anymore. Um, and E really doesn't exist. All you have is this BLM and E prime. Um, and now what I'm saying is that um, this one way to show BLM E prime are concyclic, well, there's a lot of ways. One way you can do it is by showing this equality. And the reason I chose this equality other than any other equality of angles is because I think this angle, LBM, is easy to calculate. Okay, I think you can actually calculate it exactly in this case. And that's because of how we defined L and M, right? I mean, we really just had but I mean, what do we have? We have this, we started with this K and we just reflected it twice, right? That's all we did. And that's how we get this L and M. So it should be very easy to calculate BLM. Okay, and so in fact we can do it. Um, do you see how you would do it? So maybe I'll say observe. So how would you calculate LBM? Well, it's the difference of two angles. So it's going to be a difference of, yeah, so what's the idea? Um, it's going to be LBC minus MBC, but those are just doubles of like so LB so yeah, what am I saying? So I meant to write LBK minus MBK. And then because of this reflection property, LBK is yeah, so this is going to be twice of ABK minus twice of um, CBK. So this is twice of ABC. Does that make sense? This calculation. Okay. Are people tired now? Maybe it's better if we resume this next time. I don't know.
Yeah,
Yeah. Um, yeah. Okay, yeah, so this is a long problem. I think maybe it might take more time to go over. Yeah. Um, yeah, okay. So maybe why don't we go over this next time? I will Okay, so maybe what I'll do is I will send some of the steps we've done so far as homework. Okay. Um, does that sound good?
Yes.
Yeah. Okay.
We'll be studying geometry next week.
Sorry?
Will we be studying geometry next class?
Yeah, I think it would be good if we did some more geometry. Unless, I mean, is there some other request you have for topics you'd like to
Uh,
cover?
no, I'd actually like to study more geometry.
Yeah, so let's do more geometry. Yeah, let's do more geometry. I think Friday will be our last class, right? Do you guys know when you are leaving for the IMO? You guys
It's
can
like about the 14th this month, about the 14th of this month.